As a welder, you are well trained in the procedures and techniques you must use when repairing Army vehicles, equipment, and structures. When you're deployed to regions experiencing severe cold weather, however, you also need to know the special requirements that arise when you must do your welding in the field at extreme low temperatures. In this program, you will learn how to adjust the procedures and techniques you already use in order to accomplish successful welding in extreme cold weather, and you will learn the safety precautions that apply. When you have completed your review of this program, you will be able to describe the effect of extreme cold on metals and other materials, how to preheat the weld area, how to make the weld repair using multi-pass procedures, and how to post-heat the weld repair for stress relief, all while avoiding personal injury due to extreme cold. The Army today serves in severe cold regions throughout the world, and it is a difficult, potentially hazardous environment in which to live and work. The current publication on vehicle maintenance in severe cold deals with the effects of cold weather from 0 to minus 65 degrees Fahrenheit. Higher temperatures in that range would be typical of winter in the northern continental United States, Korea, and parts of Europe, while the range from minus 25 to minus 65 degrees Fahrenheit would be encountered in Arctic regions. Severe cold weather effects on soldiers and material and on welding procedures begin to appear near zero and become critical throughout the lower range. Impact tests on steel show the radical change in ductility that occurs as temperatures approach 0 degrees Fahrenheit. At colder temperatures, steel becomes increasingly brittle. Laboratory experiments show what happens to materials at extreme low temperatures. Steel, for example, shatters on impact. Rubber, normally more or less flexible, also becomes brittle and fractures readily. Plastics also are brittle and fracture on bending or shatter on impact. Extreme cold also aggravates expansion and contraction. This can affect crack initiation and propagation in welds. Extreme cold can also cause valves and such devices as regulators to freeze up, meaning that increased gas pressures and flow rates may be required. All this means that you as a welder need to adjust your work habits and take extra precautions at the work site. Wind intensifies the hazards posed by extreme cold temperatures, meaning that to the extent possible, the work site should be sheltered from the wind. Use a swing fire or other type of heater to keep yourself and your welding equipment warm. If the shelter is enclosed, be warned of the carbon monoxide hazard. It's a killer, so make sure there's adequate ventilation while the heater is operating. To keep welding equipment such as leathers and regulators up to operating temperature, you can keep them in the vehicle cab, warmed by the personnel heater. There's another serious hazard you need to guard yourself against. The temperature of solids and liquids, cold-soaked vehicles, and other equipment is as low as the air temperature. At extreme low temperatures, touching any of these materials with bare skin could cause serious injury because the skin sticks to metal and flesh can be flash frozen in liquids. That means you must resist the temptation to work barehanded. Always wear gloves. When Arctic mittens make handwork extremely difficult, you can wear inserts for brief periods for more dexterity. Another thing to keep in mind is that the time to complete a welding repair can be 3 or 4 times longer than normal in severe cold weather. You'll be required to know how to deal with both ferrous and non-ferrous metals in extreme cold. Both require preheating and post-heating. The current publication will spell out differences in welding techniques and procedures that apply, including, for example, multi-pass welding. We'll cover some of the major ones in the next few minutes. As always, you need to know in advance the materials you'll be welding and provide the necessary tools, equipment, and supplies. You'll be arc welding metals, and the manual explains which rods are most suitable. You'll also need your oxyacetylene torch for job preparation, preheating, and post-heating. In general, job preparation is identical to that at normal temperatures. V-groove as required. Then clean the weld area to assure a good job. If rusted metal is involved, thorough cleanup is essential. Rust will add carbon to the weld area, contributing to embrittlement, so be sure to remove all rust. You'll be using electric arc welding for repairs in steel, as in the case of the crack and high carbon steel in our example here. In general, arc welding impairs the properties of steel in the area of the repair, and extreme cold aggravates the problem, for reasons we'll see in a few moments. The objective during welding is to prevent hardness and brittleness in the fusion zone that can lead to cracks like this one. To give you some idea of the nature of the problem, consider this bulldozer blade. Cold soaked until it is extremely cold, undergoing a welding repair. The base metal is at a much lower temperature than that in the weld zone and produces a quenching effect in that zone. Especially in extreme cold, the temperature change is extremely steep. Cold-soaked steel can be at minus 65 degrees Fahrenheit or more than 120 degrees lower than metal at standard day temperature, while metal in the weld zone can be in excess of 2,000 degrees. Welding heats a narrow zone on each side of the deposited metal above its critical temperature, but the metal is immediately quenched by the cold base metal. This results in a hard, brittle, non-ductile formation. It is in this zone that cracks are most likely to form as heat is suddenly applied. You need to take special precautions to minimize the formation of these hard zones so as to limit their effect on the properties of the metal. A combination of preheating, proper welding techniques, and post-heating is needed to tackle such problems. So let's see how to go about it. First of all, use a rosebud tip on the oxyacetylene torch and heat about a foot outward from the damage. As the manual shows, the amount of carbon in the steel determines the temperature to which the material must be preheated. For low carbon steel, the range goes up to 300 degrees Fahrenheit. For medium carbon steel, the range is 300 to 500 degrees Fahrenheit. For a welder, the toughest challenge is high carbon steel, with carbon content exceeding 0.55%. High carbon steel must be preheated from 500 to 800 degrees Fahrenheit. Because it's important to hit the right preheat temperature range for the material you're working with, you should use temperature sticks that melt when you've reached the proper temperature as a guide. Preheat the steel out to about 12 inches. Now use the multi-pass technique to repair the crack. Adjust welding heat to provide good fusion at the root and side walls without excessive penetration. Control welding heat by depositing metal in small string or tempering beads. Lay down beads 1 to 2 inches in length, starting at the root and toe of the groove. Avoid excessive puddling, because this will pick up carbon from the base metal, which, as we've seen, will make the weld metal hard and brittle. Confine the fusion between the filler and the base metal sidewalls to a narrow zone. Immediately peen the bead while the metal is still hot to overcome cooling stresses. The multi-pass technique offers a major advantage. Each layer of metal you deposit serves to stress relieve the bead beneath it. It will also partially temper the heat-affected zone produced in the base metal by the preceding bead. The order in which beads are laid down is important for this reason. By alternating beads, first on one side of the weld area and then the other, you gain closer control of heat input at the joint, and you can also maintain the shape of the weld better. The passes at the toe of each weld layer also serve as annealing passes, so lay these down before filling the intervening space with additional beads. These annealing passes are important because they help eliminate fusion zone cracks that might otherwise start at the surface of the weld. After you've completed the welding repair, the next step is vitally important: post-heating. Keep torching for post-heating until the temperature is at the point recommended by the manual, and then insulate the area for gradual cool down and stress relieving. The manual shows post-heating temperatures for low and medium carbon steels. They should be no higher than preheat temperatures. In our case, the repair area must be maintained at around 1200 degrees Fahrenheit. For repairs in the field, maintain this temperature for 30 to 60 minutes, a job that will be done by an insulating blanket. Otherwise, cooling may take place too rapidly at extreme cold temperatures. The purpose of stress relieving is to prevent hardness and brittleness in the fusion zone. Once cool down has been completed, carefully examine the welding repair for signs of cracking in the weld area. If sizable cracks appear, it will be necessary to groove the crack zone, as in the case of the original crack, and perform the welding repair in the same manner. In this case, we can assume that the repair was a success. For cracks in certain structures, such as frames and supporting arms, you need to add a reinforcement plate, or fish plate as it's called. Follow the guidance in the current publication for this type of repair. It's important to note that you do not continue the welding bead entirely around the plate. Making the reinforcement rigid in this way would merely transfer the stresses that caused the crack or break to the plate, leading to eventual damage in that area. Instead, confine the welding bead to the top and bottom of the plate, leaving the remaining sides unwelded. This maintains flexibility in the repair and allows it to deal successfully with continuing stresses. Now that we've reviewed welding of ferrous metals in severe cold weather, let's go on to non-ferrous metals and see what's involved. Some of your welding will be in aluminum. The use of temperature sticks will be particularly helpful when welding aluminum because there is no color change as aluminum heats up. The manual recommends preheating to between 500 and 800 degrees Fahrenheit, as in the case of high carbon steel. Post-heating for aluminum and the other non-ferrous metals is also carried out using an insulating blanket. This should continue for about 30 minutes in these metals. When soldering copper and copper alloys, such as bronze and brass, refer to the current publication for proper preheat temperatures. In this program, you have seen the effects that extreme cold can have on humans and material, and you have been shown the precautions you must take when welding in severe cold. That welding of ferrous metals in such environments requires preheating, multi-pass techniques, and post-heating to achieve successful welds. And you have also seen that welding in non-ferrous metals is similar in most respects to ferrous metals. You, as a trained welder, can achieve successful welds in extreme cold by knowing the special requirements that exist and by following them safely on the job. In severe cold as well as in the jungle, the Army needs what you do to stay in fighting trim. As a professional in the United States Army, you know it takes constant training and study to make your mark. For welding in severe cold weather, we've given you a start. Now, take it from there.